Picture a force so powerful it can rip atoms apart from thousands of miles away, a cosmic powerhouse capable of bending the very fabric of reality. This isn't science fiction. It's the reality of a neutron star's magnetic field, a force billions of times stronger than anything we've ever created on Earth. These extreme magnetic fields are some of the most violent and mysterious phenomena in the universe, warping space, distorting time, and defying our understanding of physics. And today, we're diving deep into their secrets, uncovering 30 astonishing facts about these celestial powerhouses that will leave you in awe of the universe's raw, untamed energy. What makes these magnetic fields so extreme? Imagine Earth's magnetic field as a gentle breeze barely noticeable, quietly guiding compass needles. Now picture a neutron star's magnetic field as a hurricane of unimaginable intensity, one so fierce it could strip the electrons from your body in an instant. These fields aren't just strong, they're lethal, shaping the destiny of stars, bending light itself, and even slowing down time in their vicinity. Yet they're also the universe's best-kept laboratories, revealing clues about the fundamental forces that govern everything from the tiniest particles to the largest galaxies. This video is your front-row ticket to the most extreme magnetic phenomena in existence. We'll explore how these fields twist space into knots, how they birth some of the brightest explosions in the cosmos, and why they might hold the key to unlocking new physics beyond Einstein's wildest dreams. Whether you're a space enthusiast or just curious about the universe's most extreme wonders, you're about to embark on a journey that will stretch your imagination to its limits. So buckle up, because by the time we're done, you'll never look at a magnet the same way again. The mysteries of these cosmic powerhouses are waiting. Let's begin. If Earth's magnetic field were a whisper, a Magnetars would be a sonic boom powerful enough to shatter planets. These cosmic monsters, born from the violent deaths of massive stars, pack magnetic fields so intense they defy comprehension. Just one Magnetar, like the infamous SGR 180620, boasts a field a quadrillion times stronger than our planet's. To put that in perspective, if you brought a quarter-sized Magnetar fragment within 1,000 miles of Earth, its magnetic pull would erase every credit card on the planet and probably rip satellites from orbit. But raw strength isn't even the most terrifying part. Magnetars misbehave. In December 2004, SGR 180620 unleashed a gamma-ray flare so violent it briefly outshone the entire Milky Way from 50,000 light-years away. In half a second, it released more energy than our Sun will emit in 250,000 years. That's not just a magnetic field, it's a cosmic weapon, twisting space-time so severely that photons struggle to escape its grip. Scientists call these eruptions Starquakes, where the Magnetar's crust cracks under magnetic pressure like a diamond snapping under cosmic pliers. What creates such insanity? Picture a dying star collapsing inward, its core compressing until protons and electrons merge into neutrons. Now spin that stellar corpse up to 700 times per second, while concentrating all its original magnetic energy into a sphere just 12 miles wide. The result, a magnetic dynamo so extreme it ionizes the vacuum of space around it, creating a haze of particles where empty void should exist. Even light can't escape unscathed. X-rays bend into loops near the surface, and time itself slows measurably in its presence. Yet Magnetars aren't just destroyers, they're gold mines for physicists. Their outbursts help us test Einstein's theories under conditions no lab could ever replicate. Some researchers even speculate that ancient Magnetar flares might explain mysterious radiation spikes in tree rings from the 8th century. One thing's certain, these magnetic beasts remind us that the universe operates on a scale of power we're only beginning to fathom, where a single stellar remnant can outshine galaxies and warp the very laws of physics. To understand how a Magnetar is born, we have to witness the death of a star, a spectacular, cataclysmic event more violent than anything our solar system has ever seen. When a massive star, at least 8 times heavier than our Sun, exhausts its nuclear fuel, its core can no longer resist the crushing force of gravity. In a heartbeat, the star collapses inward, triggering a supernova explosion so bright it can outshine entire galaxies. But hidden in that chaos lies the seed of a Magnetar, a neutron star with a magnetic field cranked up to unimaginable levels. The secret lies in what physicists call magnetic flux conservation. Imagine a star's original magnetic field as invisible threads woven through its core. When that star collapses from a sphere hundreds of thousands of miles wide down to a compact ball just 12 miles across, those threads don't disappear, they get squeezed tighter than the strings of a cosmic guitar. The same magnetic field that once gently influenced solar winds now becomes hyper-concentrated, its power multiplying by a factor of a quadrillion. It's like taking a refrigerator magnet and compressing it to the size of a sugar cube, only to find it now has the strength to lift an aircraft carrier. But the real magic happens in the spin. As the dying star's core collapses, it doesn't just shrink, it starts rotating faster, obeying the same physics that makes a figure skater spin quicker when pulling in their arms. Some newborn Magnetars whirl at dizzying speeds, completing a full rotation in mere milliseconds. That rapid spin, combined with a superfluid quantum soup of neutrons swirling inside, acts like a dynamo, amplifying the magnetic field even further. The result, a star so magnetically charged it can distort the atoms around it, creating exotic quantum states that don't exist anywhere else in the universe. These aren't just theoretical ideas, we've seen the evidence in real time. When supernova 1987 erupted in the Large Magellanic Cloud, astronomers detected a burst of neutrinos so intense it confirmed the birth of a compact stellar remnant. Some suspect that remnant may have been a Magnetar lying in wait, its magnetic field still intensifying as it cooled. And in 2020, researchers spotted a young Magnetar just 16,000 light-years away, spewing X-rays and radio waves with such erratic fury that it briefly became one of the brightest objects in the sky. What's truly humbling is realizing that these cosmic powerhouses are fleeting. Within 10,000 years, a blink in cosmic time, a Magnetar's magnetic field begins to fade, its energy slowly bleeding away into space. But while they last, they serve as nature's ultimate physics experiments, bending the rules of relativity and quantum mechanics in ways we're only starting to decode. Every Magnetar is a relic of stellar violence, a scar left behind by a star that refused to die quietly, and in its final act, it unleashed a magnetic storm powerful enough to redefine the extreme. On a Magnetar, even gravity, the force that binds planets and crushes stars, bows to the dominance of its magnetic field. Picture an atom caught in this cosmic tug of war. While the Magnetar's gravity is strong enough to flatten a human into a pancake in microseconds, its magnetic field is 10,000 times more powerful. At that intensity, the rules of chemistry itself break down. Electrons, which normally orbit nuclei in predictable clouds, get stretched into needle-thin lines, forced to align with the magnetic field like iron filings near a lab magnet. Even the protons inside atomic nuclei wobble under the strain, distorting matter into bizarre, elongated shapes that shouldn't exist anywhere else in the universe. This isn't just theoretical, it's visible in the light Magnetars emit. Normally, X-rays from a neutron star's surface show a smooth spectrum, but Magnetars add a jagged twist. Their magnetic fields are so overpowering that they split X-ray photons into multiple energies, a phenomenon called vacuum birefringence. It's as if light itself gets shredded by the sheer magnetic chaos, revealing fingerprints of atoms stretched beyond recognition. Under these conditions, a single sugar cube of Magnetar material would weigh billions of tons, yet its magnetic field would still dictate how every particle inside it behaves. The real surprise, Magnetars flip the script on what we consider extreme. On Earth, gravity always wins. Drop a magnet and it falls despite its magnetic pull. But near a magnetar, the opposite happens. Magnetic forces override gravity so completely that charged particles get launched into space at nearly light speed, creating fiery jets detectable across galaxies. Even space-time pays the price. The fields are so intense they generate frame dragging, where the magnetar's rotation literally twists the fabric of reality around it like a spoon stirring honey. Yet these monstrous fields aren't infinite. Push them too far and they snap back violently. Some magnetars suffer magnetic reconnection events, cosmic short circuits where field lines break and reconnect, unleashing enough energy in milliseconds to power human civilization for centuries. It's a stark reminder that in the universe's most extreme laboratories, even the mightiest forces have their limits. And for physicists, that's the real treasure. Magnetars don't just bend matter, they bend the rules, offering glimpses of what happens when nature's fundamental forces collide at the edge of impossibility. Even the surface of a magnetar isn't safe from its own magnetic chaos. Imagine Earth's crust cracking under tectonic pressure. Now amplify that by a factor of 1 billion and you've got a starquake. These aren't just tremors, they're apocalyptic ruptures where a magnetar's rigid outer layer, a crust of iron nuclei squeezed into a crystalline lattice harder than diamond, suddenly fractures under the strain of its own magnetic field. When that happens, the energy released doesn't just shake the star, it unleashes a magnetic tsunami so violent it can be detected halfway across the universe. Here's where physics gets surreal. The crust isn't breaking randomly, it's snapping because the magnetic field beneath it is twisting. Picture a rubber band stretched to its limit. The more you twist it, the more stress builds until it finally recoils. Now replace that rubber band with a magnetic field strong enough to distort spacetime, and you've got the recipe for disaster. As the field lines tangle and shear, they store unimaginable energy until the crust can't take it anymore. In a split second, the star's surface shifts by mere centimeters, but that tiny movement is enough to trigger a magnetic reconnection event where field lines rupture and explosively realign. The numbers defy belief. A single starquake can release more energy than our sun emits in 150,000 years. But unlike solar flares which spray charged particles into space, a magnetar's eruption is far stranger. The reconnection event converts magnetic energy into high-energy gamma rays and X-rays with such intensity that it briefly outshines every star in its galaxy. In March 1979, astronomers detected a gamma-ray pulse so powerful it ricocheted off the Moon and lit up detectors across the solar system, all from a starquake 50,000 light-years away. What's even wilder, these explosions aren't just brute force, they're cosmic laboratories. The reconnection process creates conditions so extreme that particles get accelerated to near light speed in microseconds, producing antimatter as a byproduct. Some theories suggest these events might even generate fast radio bursts, those mysterious intergalactic signals that have puzzled scientists for decades. And just like earthquakes, starquakes leave scars, the magnetar's surface gets permanently deformed, its magnetic field reconfigured in ways that can make future eruptions even more unpredictable. Yet for all their fury, starquakes offer a silver lining. They're our best window into the inner workings of these magnetic monsters. By studying the afterglow of these eruptions, astronomers can map the hidden structure of a magnetar's crust and field lines like cosmic seismologists decoding the echoes of a stellar heart attack. Every crack, every flare, every twisted magnetic knot is a clue to understanding how matter behaves under pressures and forces no earthly lab could ever replicate. And that's the paradox of magnetars. Their most destructive moments are also their most revealing. Some stars don't just shine, they devour. The Black Widow pulsar, officially known as PSRB 1957+20, is a cosmic predator wrapped in a magnetic field so ferocious it's slowly vaporizing its own companion star. Imagine a neutron star spinning 622 times per second, so fast its surface moves at nearly a quarter the speed of light, while its magnetic field acts like a celestial grinder, tearing apart a nearby star atom by atom. This isn't just a binary system. It's a one-sided massacre where the pulsar's lethal magnetic winds blast its companion with enough radiation to strip away 500 trillion tons of material every second. What makes this dance so deadly? The Black Widow's magnetic field doesn't just pull, it accelerates. Charged particles ripped from the companion star get funneled along field lines and whipped to near light speeds, creating a storm of high-energy gamma rays and X-rays. Think of it as a cosmic sandblaster, where the sand is actually superheated plasma capable of frying any known material to ashes in nanoseconds. Over time, this relentless erosion has reduced the companion, once a star like our Sun, to a shriveled husk barely larger than Jupiter. Astronomers call these victims Black Widow companions, stars drained to oblivion by their merciless partners. But the horror doesn't stop there. The pulsar's magnetic field also bends space itself, warping the companion's orbit into a teardrop shape. Tidal forces stretch the star's outer layers, making it easier for the pulsar to feast. And feast it does. Observations show the Black Widow's gravity slurps up stolen gas, funneling it onto its surface in fiery geysers that ignite periodic X-ray bursts. Yet even as it consumes, the pulsar's rotation slows ever so slightly, the cosmic equivalent of a predator pausing to digest, its spin sapped by the sheer mass of its own gluttony. What's truly bizarre is how quiet the carnage looks from afar. Optical telescopes see only a faint, flickering dot, its light dimmed by the pulsar's particle winds. But point a gamma-ray detector at it, and the Black Widow lights up like a flare in the dark, its emissions betraying the violence beneath. This contrast makes it a Rosetta Stone for astronomers. By studying how its magnetic field interacts with its meal, we're decoding how extreme magnetism shapes the fate of binary stars across the universe. The irony: the Black Widow might be digging its own grave. As it consumes its companion, it's running out of fuel to sustain its magnetic fury. In a few million years, a blink in cosmic time, the feast will end, leaving behind a cold, silent neutron star and the ghostly remains of what was once a thriving star system. Until then, it's a front-row seat to one of the universe's most brutal relationships, where magnetism isn't just a force, it's a weapon. Some cosmic duets aren't just harmonious, they're downright electrifying. Take Scorpii, a binary system where a spinning white dwarf acts like a colossal particle accelerator, whipping electrons to near-light speeds with its monstrous magnetic field. Unlike typical stellar pairs, this one doesn't just orbit, it performs, emitting beams of radiation so intense they light up the surrounding space like a celestial disco ball. Every 1.97 minutes, the white dwarf's magnetic poles sweep past its companion star, bombarding it with high-energy particles that generate eerie, pulsating light visible across the electromagnetic spectrum. What makes this system so mesmerizing is how it defies expectations. White dwarfs are usually stellar retirees cooling embers of dead stars, but Scorpii's dwarf is anything but quiet. Its magnetic field, 1,000 times stronger than Earth's, acts like a cosmic slingshot, flinging electrons along its twisted field lines. These particles crash into the companion star's atmosphere, creating shockwaves that emit highly polarized light that vibrates in a single plane, like sunlight reflecting off a windshield. This polarization is the smoking gun, proving the particles aren't just heating the star, they're being ruthlessly organized by the dwarf's magnetic grip. The real spectacle happens in the wavelengths our eyes can't see. As the accelerated particles spiral around magnetic field lines, they emit synchrotron radiation, the same process that lights up particle accelerators on Earth. But here, the scale is mind-bending. Electron beams with energies millions of times stronger than anything produced at CERN, dancing across a stellar stage light-years wide. The result, a lighthouse effect brighter than 1,000 suns, flickering with clockwork precision as the dwarf spins. Yet Scorpii holds an even deeper mystery. Where does its power come from? Typically, white dwarfs slow down as they age, their spin sapped by time. But Scorpii's dwarf is a frenetic whirligig, rotating once every 2 minutes, a speed that suggests it's stealing energy from its companion. This vampiric transfer might explain the system's bizarre glow, hinting at a delicate balance where the companion star's mass fuels the dwarf's magnetic fury. It's a symbiotic relationship turned predatory, proving that in the cosmos, even retirement can be anything but peaceful. For astronomers, systems like Scorpii are Rosetta Stones for understanding extreme magnetism's role in stellar evolution. They challenge our assumptions about dead stars, revealing how magnetic fields can resurrect stellar corpses into some of the universe's most dynamic performers. And as these cosmic light shows flicker across the void, they remind us that magnetism isn't just a force, it's a conductor, orchestrating some of space's most spectacular symphonies. Earth's magnetic field might seem unshakable, a steady force guiding compass needles and shielding us from solar storms, but it's had moments of cosmic indecision. Buried in ancient rocks lies evidence of our planet's magnetic identity crises, full reversals where north and south poles swap places, flipping the world's magnetic orientation like a gargantuan switch. These paleomagnetic reversals sound dramatic, but compared to the violent magnetism of neutron stars or magnetars, Earth's flips are shockingly polite. Take the most recent reversal, the Lachamp event, which happened roughly 41,000 years ago. For centuries, our planet's magnetic field weakened, flickering like a dying light bulb before finally collapsing entirely. For a few chaotic centuries, compasses would have pointed south, auroras danced near the equator, and solar radiation peppered the atmosphere, yet life carried on. No crust-shattering starquakes, no gamma-ray bursts, just a quiet recalibration recorded in volcanic rocks as iron minerals aligned with the temporary magnetic south. Even at its weakest, Earth's field never dropped below 10% of its current strength, a far cry from the trillion-fold surges of a magnetar. The secret lies in scale. Earth's magnetism comes from molten iron sloshing in its outer core, a relatively gentle dynamo compared to the quantum chaos inside a neutron star. When our field reverses, it's like a slow-motion taffy pull. Magnetic lines stretch, tangle, and eventually reorganize over thousands of years. But in Magnetars, field lines snap like over-tightened guitar strings, releasing enough energy to power supernova. Even mid-reversal, Earth's worst tantrum might briefly confuse migrating birds. Meanwhile, a Magnetar's bad day could sterilize planets light years away. Yet these reversals hold cosmic significance. They're proof that magnetism, even on planetary scales, is never static. The same forces that let Earth's field wander are the ones that, in more extreme environments, twist space and time into knots. And here's the humbling twist. If a magnetar's field flipped, the resulting energy release could vaporize nearby star systems, our paleomagnetic record. It's the universe's way of whispering that even the most familiar forces have wilder, deadlier siblings lurking in the dark. Jupiter doesn't just have a magnetic field, it has a magnetic empire. This gas giant's invisible influence stretches over 4 million miles into space, making it the largest structure in the solar system besides the Sun itself. At its core, a churning ocean of metallic hydrogen, a form of matter so exotic it behaves like both a liquid and a metal, spins at dizzying speeds, generating a magnetic dynamo 20,000 times stronger than Earth. Picture the entire planet as a cosmic power plant, where pressures 3 million times greater than our atmosphere squeeze hydrogen atoms until their electrons break free, creating a swirling, electrically conductive soup that fuels the most intense planetary magnetosphere we've ever seen. The numbers alone are staggering. Jupiter's magnetic field is so vast that if it were visible, it would appear 4 times larger than the full moon in Earth's sky despite being 500 million miles away. But what's truly terrifying is what it does with that power. The field traps charged particles from the solar wind, whipping them into radiation belts so intense they'd fry spacecraft electronics in hours. These are the solar system's ultimate minefields, donut-shaped zones of death called Van Allen belts, but scaled up to Jovian extremes. One passed through the densest region, and an unshielded astronaut would absorb a lethal dose in minutes, not from solar radiation, but from Jupiter's own particle accelerators, where electrons scream along field lines at nearly light speed. Why such ferocity? It's all in the spin. Jupiter rotates once every 10 hours faster than any other planet, turning its metallic hydrogen core into a superconductive whirlpool. This rapid motion, combined with convection currents hotter than the Sun's surface, creates a magnetic feedback loop more chaotic than Earth's orderly dynamo. Probe data reveals the field isn't even symmetrical, it's lopsided, with a dent near the equator where magnetic lines kink violently. Some theorists believe this asymmetry hints at hidden structures deep within Jupiter's core, perhaps even a layer of helium rain or a rocky inner core stirring the metallic hydrogen like a spoon in a cosmic cup. Yet Jupiter's magnetic might isn't just destructive, it's transformative. The same radiation belts that spell doom for spacecraft also ignite the planet's polar auroras, which outshine Earth's northern lights by a factor of 100. These aren't gentle glows, they're continent-sized storms of ultraviolet fury, powered by particles crashing into the atmosphere at energies that would make CERN Collider blush. And when Jupiter's volcanic moon, Io, spews sulfur dioxide into space, its magnetic field grabs the gas and ionizes it into a donut of plasma along the moon's orbit, a glowing halo of charged particles visible from Earth with backyard telescopes. What's humbling is realizing Jupiter's field isn't static, it pulses. Every few decades, the planet emits bizarre radio bursts called decametric radiation, howls of energy so predictable they were used to calibrate early space probes. These bursts are the sound of magnetic field lines snapping like cosmic whips, flinging electrons in chaotic spirals. Even now, Juno spacecraft data suggests the field might be slowly shifting, its poles migrating like Earth's, but on a scale befitting the king of planets. One day, Jupiter's north could become its south, rewriting the rules of its magnetosphere in a planetary flip we're only beginning to understand. For astronomers, Jupiter is both a shield and a laboratory. Its field deflects deadly cosmic rays that might otherwise reach the inner solar system, while its extremes let us test theories about magnetic dynamos under conditions impossible to replicate on Earth. And as we stare at those swirling auroras, we're reminded, magnetism isn't just a force, it's the invisible hand shaping worlds, turning gas and spin into a cosmic protector and a lethal prison. The sun may look like a smooth ball of fire, but zoom in close and you'll find its surface is pockmarked with dark, planet-sized blemishes, sunspots. These aren't just cosmetic flaws, they're battle scars from the sun's tangled magnetic warfare. Each spot is a cosmic prison where magnetic fields 1,000 times stronger than Earth's clamp down on the sun's boiling plasma, strangling the convection that normally makes the surface blisteringly hot. The result, a region that glows at 4,000 degrees Celsius, still scorching, but noticeably cooler than the surrounding 5,500 degree plasma. That temperature drop is why sunspots appear black to our eyes, like holes burned into a neon sign. But the real danger lies in what happens when these magnetic shackles break. Sunspots form where the sun's internal magnetic field lines, stretched and twisted by the star's differential rotation, punch through the surface like a coiled spring bursting through a mattress. The tension builds invisibly until snap, the field lines reconnect explosively, releasing enough energy to power humanity for millions of years. We call these eruptions solar flares or coronal mass ejections, and they're the solar system's most spectacular tantrums. The largest can fling billions of tons of charged particles into space at millions of miles per hour, with magnetic fields strong enough to compasses on Earth. What's wild is how fast this drama unfolds. A modest sunspot might last a week, but the magnetic reconnection that triggers a flare happens in minutes. Satellite observations show magnetic loops rising hundreds of thousands of miles above the surface, then collapsing in a violent implosion that superheats plasma to tens of millions of degrees. The afterglow, X-rays so intense they can briefly outshine the entire sun in certain wavelengths, while radio telescopes pick up the eerie screech of electrons spiraling along fractured field lines. Yet for all their fury, sunspots follow a rhythm. Their numbers rise and fall in an 11-year solar cycle, tied to the slow reversal of the sun's global magnetic field. During solar maximum, the sun's face becomes a battlefield of spots, flares, and eruptions. At minimum, it may go weeks without a single blemish. This cycle isn't just celestial housekeeping. It's a reminder that even the sun dances to magnetism's tune, its fiery temper dictated by invisible forces churning beneath its surface. And when those forces unleash a direct hit on Earth, the consequences range from dazzling to disastrous. A moderate flare might paint polar skies with auroras visible as far south as Florida. But a Carrington-level event like the 1859 storm that set telegraph wires ablaze could today knock out power grids and satellites for months. Ironically, the same magnetic fields that create sunspots' darkness also birth the light shows and blackouts that remind us the sun isn't just a star. It's a magnetic powerhouse, and its moods shape the fate of every planet in its grip. Every 11 years, the sun throws a cosmic tantrum, not with explosions or outbursts, but with a silent, planet-shaking reversal of its magnetic identity. This is the solar cycle, a rhythmic heartbeat of magnetic chaos where the sun's north and south poles trade places, rewriting the rules of our solar system's largest magnetic field. Unlike Earth's erratic pole flips, which can take thousands of years, the sun's reversal is clockwork, a predictable yet violent metamorphosis that fuels everything from auroras to satellite-killing radiation storms. The engine behind this cycle is the sun's internal dynamo, a churning cauldron of plasma where heat, rotation, and magnetism conspire to create a self-sustaining magnetic furnace. Deep within the sun's convective zone, superheated gas rises and falls like water in a boiling pot, twisting the star's magnetic field lines into knots. Over time, these tangled lines erupt through the surface, forming sunspots, those dark, magnetically active regions where solar flares are born. But here's the twist. As the cycle progresses, the sun's differential rotation, its equator spinning faster than its poles, stretches these magnetic knots eastward until they snap, unleashing waves of energy that gradually push the entire magnetic field toward reversal. The climax arrives at solar maximum, the peak of the 11-year cycle. Sunspots proliferate like storm clouds, and the sun's magnetic field grows so disorganized that its poles don't just weaken, they vanish for a brief, chaotic period. Then, like a cosmic compass resetting, new polarity emerges. The North Pole becomes south and vice versa. Remarkably, this flip isn't isolated to the surface. NASA's Solar Dynamics Observatory has tracked magnetic waves propagating through the sun's corona, proving the reversal is a whole star event with consequences stretching billions of miles into space. Those consequences space weather the invisible tempests that shape life on Earth. During solar maximum, the sun's rewiring triggers frequent flares and coronal mass ejections, hurling magnetized plasma toward planets. In 2012, a near-miss ejection ripped through Earth's orbit at over 2,000 kilometers per second. Had it struck, it could have knocked out global power grids for years. Yet these storms also paint the skies. The same magnetic upheaval that threatens technology supercharges the auroras, transforming them from polar whispers to continent-spanning spectacles visible as far south as Cuba. What's fascinating is how messy the process is. The sun's hemispheres don't flip in sync. One pole often races ahead while the other lags, creating temporary magnetic imbalances. Sometimes the cycle stutters. The most recent solar minimum from 2018 to 2019 was the deepest in a century, with 281 consecutive spotless days. Theories suggest a slower conveyor belt of plasma beneath the sun's surface might have delayed the dynamo, proving even stellar magnetism obeys no perfect schedule. For scientists, tracking the solar cycle is like predicting the mood swings of a giant radioactive toddler. Satellites like Parker Solar Probe dive into the sun's corona, measuring magnetic fluctuations that could one day help forecast solar storms with the same accuracy as hurricanes. Because while the sun's 11-year rhythm might seem distant, its magnetic tantrums are anything but. They're a reminder that Earth orbits not just a star, but a seething magnetic powerhouse with the power to flicker lights or plunge civilizations into darkness. Galaxies aren't just islands of stars, they're colossal whirlpools of magnetism, where invisible fields stretch for tens of thousands of light years, sculpting cosmic dust and bending the paths of cosmic rays. The Milky Way's magnetic field alone is a sprawling web of force, threading through spiral arms with the delicate precision of a spider's silk, yet powerful enough to shape the birth and death of stars. Unlike the chaotic eruptions of Magnetars or the rhythmic flips of the sun, galactic magnetism operates on a scale so vast it orchestrates the motion of entire nebulas, turning interstellar space into a symphony of aligned particles and polarized light. How does something so immense and ordered emerge from the chaos of exploding stars and swirling plasma? The secret lies in the interstellar medium, the thin soup of gas and dust between stars. Supernovae act as cosmic mixers, stirring this soup with shockwaves that compress and twist magnetic field lines, while rotating galaxies stretch them like taffy into colossal spiral patterns. Over millions of years, these turbulent motions organize scattered fields into a coherent structure, a process called dynamo amplification. Picture an orchestra tuning up. At first, it's just noise, but gradually, the instruments synchronize into harmony. That's the Milky Way's magnetic field, a harmony forged from supernova cacophony. We can't see these fields directly, but their fingerprints are everywhere. Look at polarized starlight photons that vibrate in a single plane after passing through magnetically aligned dust grains, or trace the eerie glow of synchrotron radiation emitted by electrons spiraling along galactic field lines at nearly light speed. These clues reveal a labyrinth of magnetic corridors, some so strong they deflect high-energy cosmic rays away from star-forming regions like invisible shields. In the Milky Way's halo, towering magnetic loops arc hundreds of light-years upward, relics of ancient stellar explosions that left their mark on the galaxy's magnetic skeleton. What's astonishing is how stable these fields are. Despite the violence of their birth, galactic magnetic structures can persist for billions of years, a testament to the universe's ability to forge order from chaos. They're not static, though recent observations show fields near the galactic center twist like DNA, warped by the supermassive black hole's gravity. And in colliding galaxies, magnetic fields can snap and reconnect, triggering bursts of star formation or funneling gas into voracious black holes. Yet for all their power, these fields are fragile on a cosmic scale. The energy density of the Milky Way's magnetic field is 1,000,000 times weaker than Earth, so faint that a kitchen magnet could overpower it locally. But spread across 100,000 light-years, that faint force becomes an architect of the cosmos, guiding the birth of stars, the flow of gas, and even the journey of life's building blocks across the galaxy. It's a reminder that magnetism doesn't just shape stars and planets, it weaves the fabric of galaxies themselves. Cosmic rays, those high-energy particles streaking through space at nearly light speed, don't just wander the galaxy aimlessly. They're catapulted across interstellar distances by some of the most extreme magnetic fields in existence, the turbulent aftermath of supernova explosions. When a massive star detonates, it doesn't just leave behind a remnant, it creates a chaotic playground of magnetic fury, where shockwaves ripple through space at thousands of kilometers per second, turning the wreckage into a natural particle accelerator dwarfing anything humans could build. Take the Crab Nebula, the shattered remains of a star observed exploding in 1054. Its heart spins 30 times per second, a pulsar whipping magnetic fields into a frenzy. These fields trap electrons and protons, whirling them like marbles in a cosmic tornado, until the particles break free with energies millions of times greater than those in CERN's Large Hadron Collider. But here's the twist: unlike lab accelerators, which guide particles along neat beams, supernova remnants fling them in all directions. Some cosmic rays escape into the void, riding magnetic highways that stretch clear across the Milky Way. Others slam into gas clouds. Sparking gamma ray glows visible from Earth, ghostly evidence of invisible particles colliding at unimaginable speeds. The process works like a cosmic ping-pong game. As shockwaves from the supernova plow through surrounding gas, they create regions where magnetic fields pile up like tangled spaghetti. Charged particles bounce between these field lines, gaining energy with each pass, a mechanism called Fermi acceleration. Picture a surfer catching wave after wave, each one adding to their speed until they're rocketing forward at a significant fraction of light speed. Now imagine that surfer is a proton, and the waves are magnetic shock fronts hotter than the sun's core. That's how a humble hydrogen nucleus transforms into a cosmic ray capable of piercing spacecraft hulls or lighting up Earth's atmosphere as a dazzling aurora. What's wild is how long these particles can travel. Some cosmic rays detected on Earth have been journeying for millions of years, zigzagging across galactic magnetic fields until they finally spiral down through our atmosphere. Their origins, likely supernova that exploded before humans walked the Earth, perhaps even before the Sun formed. These are the universe's ultimate time travelers, carrying fingerprints of ancient stellar catastrophes. Yet despite their power, cosmic rays rarely travel in straight lines. Galactic magnetic fields bend their paths so severely that by the time they reach us, their trajectories are scrambled, leaving astronomers to play detective, tracing them back to likely sources like Tycho's supernova remnant or the Vela pulsar. The irony: these particles, born from destruction, might be key to creation. When cosmic rays rip through molecular clouds, they ionize gas, triggering the collapse of dense pockets that birth new stars and possibly planets. Some theories even suggest cosmic rays influenced early Earth's chemistry, potentially playing a role in the origins of life. So next time you see the northern lights shimmering, remember, you're witnessing the final act of a stellar explosion that happened light years away, its magnetic fury still writing its signature across the sky. Before a star shines, it must feast, and its most powerful dining utensil isn't gravity but magnetism. Take T-Tauri stars, the fiery toddlers of the stellar world, still gorging on gas from their birth clouds. These young stars don't just passively suck in material, they wield magnetic fields like cosmic traffic cops, funneling interstellar fuel with terrifying precision. Imagine a whirlpool where the water doesn't just spiral inward. It gets whipped into organized lanes by invisible forces, accelerating toward the star's surface at hundreds of kilometers per second. That's the power of a protostar's magnetic field, turning chaos into a controlled banquet. Here's how the magic works. As a T-Tauri star spins, its magnetic field lines act like twisted ropes, plunging into the surrounding accretion disk, a frisbee of gas and dust where planets might one day form. Where these lines puncture the disk, they create hot spots of ionized gas, magnetically glued to the star's rotation. The result: material doesn't just fall onto the star, it rides the field lines like a cosmic monorail, shooting toward the poles in fiery columns called accretion flows. Telescopes have caught these streams in action, glowing with X-rays as they slam into the protostar's surface at temperatures hotter than lava. But this feast isn't endless. The star's own magnetism regulates it. T-Tauri stars are notorious for their violent mood swings, brightening or dimming unpredictably. Why? Their magnetic fields occasionally buckle under the strain, snapping like overstretched rubber bands in events called magnetic reconnection flares. When this happens, the star temporarily shuts off its food supply, causing dramatic dips in brightness. Then, just as suddenly, the field restructures itself and the feast resumes. It's a stellar version of toddler table manners, messy, impulsive, and governed by forces far beyond the star's control. What's truly mind-bending is the scale. A typical T-Tauri star's magnetic field stretches millions of miles, enough to engulf our entire solar system out to Saturn. Yet it orchestrates flows of material so precise they'd put Swiss watches to shame. Some observations even suggest these fields act as cosmic bouncers, flinging away excess gas that might otherwise smother the star's growth. Without this magnetic regulation, young stars might either starve or choke on their own gluttony, never igniting the nuclear fires that make them shine. For astronomers, these stellar toddlers are more than just curiosities, they're blueprints. The same magnetic processes shaping T-Tauri stars likely governed our sun's infancy and possibly determined how much material was left over to build Earth. Every flicker, every flare, every magnetic tantrum is a clue to how stars and their planetary systems are born. And that's the irony. The very forces that feed a young star's growth might also decide whether it ever gets neighbors. If you charted the sun's tantrums over time, they'd paint wings, not of a celestial bird, but of a magnetic butterfly. This is the butterfly diagram, one of the most mesmerizing patterns in solar science, revealing how sunspots don't just appear randomly, but march toward the sun's equator in a slow, precise dance over each 11-year cycle. Picture a time lapse of the sun's face. Early in the cycle, sunspots erupt at mid-latitudes around 30 degrees north and south. As years pass, they creep closer to the equator, leaving behind a trail of activity that, when plotted on a graph, sketches the delicate wings of a butterfly across centuries of data. What's driving this migration? The answer lies beneath the sun's fiery surface, where a conveyor belt of plasma, superheated, electrically charged gas, slowly ferries magnetic fields from the poles toward the equator. This isn't a smooth ride. The sun's differential rotation, with its equator spinning faster than its poles, stretches and twists these magnetic fields like taffy. Over time, the fields grow so tangled they burst through the surface as sunspots, first at higher latitudes, then lower as the plasma flow drags them equatorward. It's a cosmic game of tug-of-war, where magnetism and motion conspire to create order from solar chaos. The butterfly diagram isn't just pretty, it's a decoder ring for solar mysteries. By tracking these patterns, scientists realize the sun's magnetic cycle isn't just 11 years long, it's 22. That's because the sun's polarity flips with each cycle, meaning it takes 2 full butterfly patterns, 2 11-year stretches, for the magnetic field to return to its original state. This duality hints at deeper rhythms in the sun's dynamo, the hidden engine that powers its magnetism. Yet even butterflies have scars. During the Maunder minimum, a 70-year lull in solar activity from 1645 to 1715, the butterfly diagram shrank to near invisibility. Sunspots vanished, leaving the diagram's wings clipped an eerie silence that coincided with Earth's little ice age. Modern analysis suggests the sun's plasma conveyor stalled during this period, stranding magnetic fields at the poles instead of ferrying them equatorward. It's a stark reminder that the butterfly's flight isn't guaranteed sometimes. The sun's magnetic heartbeat skips. Today, satellites like SOHO and Solar Dynamics Observatory watch this dance in real time, mapping magnetic waves as they ripple toward the equator. Each butterfly pattern is a fossil record of the sun's hidden turbulence, written in the language of sunspots. And as we decode these wings, we're not just tracing solar cycles, we're glimpsing the pulse of a star that, for all its fury, moves with a rhythm as graceful as a butterfly's flutter. Earth's magnetic field isn't just a shield, it's a living, breathing entity that occasionally throws its own cosmic tantrums. When solar wind packed with charged particles slams into our magnetosphere, it doesn't just bounce off harmlessly. Instead, the field lines stretch like rubber bands, storing energy until snap. They rupture and violently reconnect in a process called magnetic reconnection. It's the same physics that powers solar flares and Magnetar eruptions, only playing out right over our heads on a scale we can almost touch. Picture a tug of war between Earth's magnetic field and the Sun's fury. As solar wind buffets our magnetosphere, it drags the planet's field lines backward, creating a long tail on the night side, a stretched-out reservoir of pent-up energy. When the tension becomes too much, the field lines fracture and realign, launching charged particles toward Earth at blistering speeds. These particles then spiral down the newly reconnected lines like marbles on a roller coaster, slamming into the upper atmosphere near the poles. The result, auroras, nature's neon light show, where oxygen and nitrogen atoms glow crimson and emerald as they're bombarded by this invisible rain of solar debris. But reconnection isn't just about pretty lights, it's a cosmic power switch. A single event can release enough energy to power New York City for months, all in a matter of seconds. Satellites like NASA MMS mission have flown straight through these explosions, measuring how electrons accelerate to near light speed as field lines whip apart. The data reveals something astonishing. The process is fractal, meaning it happens in miniature bursts within larger ones, like a cascading chain reaction. This isn't just physics, it's a chaotic ballet where order emerges from the very moment of rupture. The irony, the same process that creates auroras can also cripple our technology. During the 2003 Halloween storms, reconnection events triggered blackouts in Sweden and fried transformers in South Africa. GPS signals wobbled and satellites tumbled blindly as the magnetosphere convulsed. Yet without this magnetic drama, life might not exist at all. Reconnection helps Earth shed excess solar energy, preventing our atmosphere from being slowly stripped away like Mars. It's a reminder that even destruction can be creative. On a cosmic scale, chaos and beauty are two sides of the same coin. What's truly humbling is realizing we're watching the universe's favorite trick in miniature. The same reconnection that lights our skies also powers quasars 1 billion times brighter than the Sun. Earth's magnetosphere is a classroom where we can study these extreme events up close, decoding secrets that govern everything from star formation to black hole jets. So next time you see the northern lights ripple overhead, remember, you're witnessing a scaled-down supernova, a fleeting echo of the magnetic fury that shapes the cosmos. When a Magnetar erupts, the blast doesn't just vanish into the void. It paints the cosmos with ghostly afterimages that linger for years. Take SGR 1900 plus 14, a Magnetar 50,000 light-years away that unleashed a cataclysmic flare in August 1998. For a fraction of a second, its gamma ray burst outshone the full moon. But the real magic happened afterward, as X-rays from the explosion began illuminating vast clouds of interstellar dust, creating rippling rings of light that expanded outward like echoes in a cosmic canyon. Astronomers watched in awe as these ethereal halos grew larger year after year, a slow-motion replay of violence frozen in space and time. This light echo phenomenon works like a stellar sonar. When the Magnetar's X-rays hit dust grains, some as small as smoke particles, they scatter in all directions. But only the rays bouncing toward Earth reach our telescopes, creating the illusion of glowing rings growing outward. The geometry is precise. Dust closer to us lights up first, while more distant clouds create delayed rings. By tracking their expansion, scientists can map the invisible architecture of interstellar space with unprecedented detail. In SGR 1900+14's case, the echoes revealed hidden dust layers 25 light-years across structures otherwise too faint to detect. What's astonishing is the timescale. Unlike supernova remnants which fade within weeks, Magnetar light echoes unfold decades later. In 2005, 7 years post-eruption, NASA Chandra X-ray Observatory spotted 4 distinct rings around the same Magnetar. By 2008, a 5th appeared. Each ring was a fossilized snapshot of the explosion's energy interacting with dust at different distances. It's as if the Magnetar stamped its fury onto the galaxy's scaffolding, leaving behind a celestial fingerprint for astronomers to decode. But these echoes aren't just pretty, they're cosmic measuring tapes. The exact spacing between rings lets scientists calculate the Magnetar's distance with razor precision, while variations in brightness expose the dust's composition. Some rings even flicker as they pass behind interstellar gas clouds, betraying the presence of otherwise invisible matter. For researchers, it's like turning the galaxy into a giant physics lab, where a single flare illuminates the universe's hidden architecture. The most poetic twist, the echoes outlive their creator. Long after the Magnetar's flare fades from memory, its light still bounces between the stars, a testament to how even the universe's most violent moments ripple through time and space. And as we watch these ghostly rings expand, we're not just seeing radiation, we're witnessing the afterlife of a star's scream. At a Magnetar's surface, the rules of quantum physics don't just bend, they shatter. With magnetic fields strong enough to twist the very fabric of the quantum vacuum, these cosmic monsters create conditions so extreme that empty space itself becomes a seething cauldron of phantom particles. Normally, the vacuum is thought of as nothingness, a void where particles only pop in and out of existence fleetingly. But in a Magnetar's grip, the vacuum polarizes, warping into an exotic state where virtual particles, the universe's quantum shadow dancers, get yanked into semi-permanent reality. This phenomenon, called vacuum birefringence, transforms the vacuum into a cosmic hall of mirrors. Photons traveling through it don't just move in straight lines, they split into 2 distinct paths based on their polarization, like light refracting through an otherworldly prism. The effect is so pronounced that X-rays emitted from a Magnetar's surface carry telltale distortions, quantum fingerprints, revealing how space itself has been magnetically scrambled. In 2016, astronomers analyzing X-rays from Magnetar 4U0142+61 found the first observational evidence of this effect, proving that even the void isn't empty when magnetism rewrites the rules. But the real madness happens when these fields pluck particles from nothingness. According to quantum theory, particle-antiparticle pairs constantly flicker into existence for infinitesimal moments before annihilating. A Magnetar's field, however, can stretch these phantom particles apart before they vanish, granting them stolen moments of real existence. The stronger the field, the longer these particles survive, like cosmic thieves escaping with borrowed time. Some theories suggest Magnetars might even spawn magnetic monopoles, hypothetical particles with a single magnetic pole that don't exist under normal conditions. It's as if the Magnetar's field bull is the quantum world into revealing secrets it would never surrender otherwise. The implications ripple far beyond stellar oddities. If vacuum polarization can be studied in Magnetars, it might help solve one of physics' greatest mysteries, unifying quantum mechanics with gravity. Magnetars are nature's only laboratories where both quantum effects and extreme space-time curvature coexist, offering clues about how these frameworks mesh. Every X-ray flare, every distorted photon is a data point in an experiment no human could ever recreate, a glimpse into the universe's most forbidden physics played out on a galactic stage. Yet the most haunting thought, these quantum distortions might leave eternal marks. As polarized photons escape the Magnetar's grip, they carry encoded information about the vacuum's altered state across the cosmos. Billions of years from now, long after the Magnetar itself has faded, these light echoes might still whisper to civilizations we can't imagine, telling tales of a star so magnetic it bent the void itself. Long before galaxies spun and stars ignited, the newborn universe might have been threaded with invisible magnetic fields, not as gentle whispers, but as cosmic scaffolding strong enough to shape the destiny of matter itself. This is the magnetic universe hypothesis, a radical idea suggesting that primordial magnetism didn't just tag along during cosmic evolution, it directed it. Picture the universe in its first trillionth of a second, a seething plasma so dense that light couldn't travel freely. According to this theory, microscopic magnetic fields already existed in that chaos, woven into the fabric of space-time like faint cosmic brushstrokes. Then came inflation, the universe's explosive growth spurt, which stretched these fields from subatomic scales to intergalactic sizes in less than a blink. What started as quantum fluctuations could have become titanic magnetic ropes, crisscrossing the early cosmos with invisible force. But how could something as delicate as a magnetic field survive the universe's violent birth? The answer lies in plasma's stubbornness. In those early moments, the universe was too hot for atoms, just a soup of charged particles that conducted electricity like a superconductor. Magnetic fields, once created, couldn't easily dissipate. They were frozen into the plasma like fossils in amber. As the cosmos expanded and cooled, these fields didn't fade. They stretched, thinning out but never breaking. By the time the first stars flickered to life, these primordial fields might have spanned hundreds of thousands of light years, invisible threads tugging matter into the patterns we now recognize as galaxy clusters and cosmic webs. The evidence looked no further than today's galaxies. Many, including our Milky Way, harbor large-scale magnetic fields aligned with their spiral arms, fields too vast and organized to have formed solely from local stellar processes. Some theorists argue these are cosmic heirlooms, remnants of those primordial fields preserved over 13 billion years. Even more telling, astronomers detect weak but coherent magnetic fields in the voids between galaxies where there's hardly any matter to generate them. These intergalactic fields, measured by observing how they twist the polarization of light from distant quasars, shouldn't exist unless they're relics of the universe's infancy. Yet the boldest claim of the magnetic universe hypothesis isn't just about preservation, it's about creation. Computer simulations show that primordial fields could have acted as cosmic gathering points, their subtle tensions nudging gas clouds into denser knots where gravity later took over. Without magnetism's gentle guidance, matter might have remained too diffused to collapse into galaxies efficiently. In this view, magnetism wasn't a bystander to cosmic evolution. It was the invisible hand that stacked the deck for structure to form. Critics point out the gaps. No one yet knows how those initial fields arose, though some speculate they were born from quantum fluctuations during inflation or phase transitions in the early universe's cooling. Others argue that even inflated fields would have been too weak to significantly influence galaxy formation. But supporters counter with a cosmic coincidence. The energy density of today's large-scale magnetic fields matches predictions of what primordial fields stretched by inflation would look like. It's as if the universe left a coded message in magnetism's strength, a clue waiting to be deciphered. The hunt for proof is on. New radio telescopes like the Square Kilometre Array aim to map the universe's magnetic skeleton in unprecedented detail, searching for patterns that could only stem from primordial origins. Meanwhile, physicists study tabletop experiments with ultra-cold quantum gases, simulating how magnetic fields might have behaved in the early cosmos. Every discovery inches us closer to answering a profound question. Did magnetism, often overshadowed by gravity's might, secretly orchestrate the universe's grand design? If the magnetic universe hypothesis holds, it would rewrite cosmology's origin story. No longer just a side effect of stars and plasma, magnetism would take its place alongside gravity and dark matter as a foundational architect of cosmic structure. And those faint magnetic whispers we detect today, they'd be echoes of the universe's first moments, a silent, invisible blueprint imprinted on everything from swirling galaxies to the vast voids between them. At the heart of every active galaxy, a supermassive black hole feeds on swirling gas with such violence that it can outshine entire galaxies, but the real spectacle isn't just the feast. It's the way magnetic fields twist this chaos into precision-engineered jets, launching matter across millions of light-years at nearly light speed. These aren't just streams of particles, they're cosmic particle accelerators wrapped in magnetic coils so intense they distort space-time itself, bending light like a funhouse mirror on a galactic scale. Picture an accretion disk, a whirlpool of superheated plasma orbiting the black hole, as a cosmic dynamo. As gas spirals inward, friction heats it to millions of degrees, ionizing atoms into a soup of charged particles. But here's where magnetism takes center stage. The disk's rotation, combined with turbulent plasma motions, twists magnetic field lines into helical coils. These coils don't just sit idly, they act like cosmic railguns, funneling material away from the disk's poles in narrow, magnetically collimated jets. The process, called the Blandford-Zenagic mechanism, converts the black hole's spin energy into jet power, threading those outflows with magnetic fields strong enough to launch particles beyond the galaxy's edge. The sheer scale of these jets defies imagination. In Galaxy M87, home to the first black hole ever imaged, the jet stretches 5,000 light-years, a filament of plasma so precisely focused it barely widens over that distance. Magnetic fields keep it tight, preventing the jet from dispersing like smoke in the wind. But the real magic happens where the jet interacts with intergalactic space. Shockwaves ripple through the jet's magnetic sheath, accelerating electrons to such extreme energies that they emit synchrotron radiation light polarized in a telltale pattern that betrays the magnetic field structure. What's truly mind-bending is how these fields warp reality. Near the jet's base, magnetic forces are so intense they create birefringence, splitting light into two paths based on its polarization. Photons traveling along the field lines move differently than those crossing them, as if space itself becomes a crystal under magnetic strain. In some active galaxies, this effect distorts the appearance of the jet, making it appear to spiral or even knot as light wrestles with the field's grip. Astronomers have even spotted jets that seem to curve back toward their source, an illusion caused by magnetic lensing bending the light's path like a cosmic mirage. Yet these jets aren't just cosmic curiosities, they're galactic architects. When they plow into intergalactic gas, they trigger shock waves that can ignite or quench star formation in entire galaxy clusters. Some theories suggest that without these magnetized outflows, galaxies like our Milky Way might never have formed, their growth stifled by overheated gas. The irony, the same black holes that devour matter also use magnetism to sculpt the universe around them, proving that even destruction can be creative on a cosmic scale. For astronomers, these jets are natural laboratories for physics at its most extreme. They've helped confirm predictions of general relativity, revealed how magnetic fields can extract energy from spinning black holes, and even hinted at how information might escape a black hole's grip, clues to solving the infamous information paradox. And as we stare at these luminous threads stretching across the cosmos, we're seeing more than just plasma. We're witnessing the invisible hand of magnetism, shaping the universe one jet at a time. Black holes have long been considered the ultimate cosmic vacuum cleaners. Anything crossing their event horizon, including light and information, vanishes forever. But what if these gravitational monsters aren't quite as bold as Einstein's equations suggest? Recent breakthroughs in theoretical physics suggest black holes might sport what researchers playfully call magnetic hair, faint but stubborn traces of external magnetic fields clinging to their surfaces like cosmic static cling. This isn't just a quirky detail, it's a potential revolution in how we understand spacetime's most destructive objects. Classical physics told us black holes should be simple, defined only by mass, spin, and charge with no other visible features, a principle cheekily dubbed the no-hair theorem. But the universe loves exceptions. When astrophysicists modeled how real-world black holes interact with surrounding magnetic fields like those from accretion disks or nearby stars, they found something startling. Instead of completely swallowing these fields, black holes might remember them, imprinting their patterns onto the event horizon in subtle, potentially detectable ways. Imagine dunking a basketball in ink and pulling it out while most ink drips away, a faint coating remains. Similarly, a black hole's spin and gravity could stretch and freeze magnetic field lines at its surface, preserving a ghostly fingerprint of its cosmic environment. The smoking gun, simulations of merging black holes. When two black holes collide, their combined event horizon doesn't just smoosh together like dough, it vibrates, emitting gravitational waves. Researchers noticed these waves might carry faint echoes of the pre-merger magnetic fields, like ripples in a pond reflecting the shape of skipped stones. Telescopes like LISA, set to launch in the 2030s, could detect these echoes, revealing whether black holes truly are as bare as we thought, or if they've been hiding magnetic secrets all along. But here's where it gets stranger. This hair isn't just a passive scar, it could function. Some theories suggest these residual fields might help launch jets of plasma from active black holes, acting like cosmic railgun guides for particles fleeing the accretion disk. Others speculate they could even influence how black holes evaporate over quadrillion of years via Hawking radiation. If magnetic hair exists, it means black holes aren't just tombs for information. They're archivists preserving clues about their past interactions in ways we're only starting to decipher. The implications ripple beyond astrophysics. If magnetic hair is real, it hints at deeper connections between gravity and quantum mechanics, two frameworks famously at odds. Quantum theory suggests information can't truly vanish, while general relativity insists black holes erase it. Magnetic hair might be the missing link, a subtle mechanism for preserving data in spacetime's most hostile environment. For physicists, that's not just a new feature of black holes, it's a potential backdoor into a theory of everything. So while Einstein's equations aren't wrong, they might be incomplete. Black holes could be far more textured and far more revealing than we ever imagined. And as telescopes grow sharper, we may soon glimpse the first strands of this cosmic hair, unraveling mysteries about how black holes grow, merge, and perhaps even how they whisper their stories across the ages. Hot Jupiter's gas giants orbiting perilously close to their stars aren't just scorched versions of our solar system's largest planet. Many might wield magnetic fields so intense they transform their own atmospheres into glowing, bloated halos, with auroras so brilliant they could be spotted from another star system. Imagine a world where the sky isn't just lit by its sun, but by its own magnetic fury, curtains of light dancing not at the poles, but wrapped around the entire planet like a luminous cage. These aren't just hypothetical scenarios. Observations of exoplanets like HD 189733b suggest some hot Jupiters experience atmospheric heating so extreme it can only be explained by the tug of war between stellar winds and a planetary magnetic field on overdrive. The physics behind this spectacle is both elegant and violent. A typical hot Jupiter orbits so close to its star that it's tidally locked, one side forever bathed in searing light, the other shrouded in eternal night. This creates a temperature gradient that, combined with the planet's rapid rotation, churns its metallic hydrogen core into a frenzied dynamo. The result: magnetic fields thousands of times stronger than Jupiter's, capable of punching back against the star's relentless solar wind. In some cases, the field acts like a cosmic shield, diverting charged particles into colossal auroral rings. In others, it becomes a trap, squeezing the planet's own atmosphere into magnetically inflated bubbles that stretch tens of thousands of miles into space, visible as extended hazes in transit observations. What's truly bizarre is how these fields might sound. If we could convert the interactions between a hot Jupiter's magnetic field and its star's plasma winds into audio, it would resemble a cacophony of cosmic static, punctuated by bursts of radio waves as magnetic reconnection events rip through the planet's magnetosphere. In fact, radio telescopes have already caught hints of this phenomenon. When the hot Jupiter HDP 11b transited its star, astronomers detected spikes in radio emissions likely caused by magnetic interactions, a potential scream from a world caught in a perpetual magnetic storm. But the real showstopper, the auroras. On Earth, our modest magnetic field creates polar lights when solar particles collide with atmospheric gases. On a hot Jupiter with an ultra-strong field, auroras could engulf the entire planet, ignited not just by stellar winds but by volcanic moons spewing plasma into space, or even by the planet's own atmosphere boiling away under the star's heat. The colors would be otherworldly, deep ultraviolet and X-ray emissions far beyond what human eyes could see, but dazzling to telescopes. And because these planets are so close to their stars, their auroras might pulse in sync with stellar flares, creating a light show choreographed by magnetic chaos. Yet these extreme fields come at a cost. Some hot Jupiters may be literally tearing themselves apart, their magnetic dynamos generating so much internal heat that their atmospheres puff up like overinflated balloons, shedding mass into space. Others could experience magnetic braking, where their fierce fields interact with the star's plasma so strongly that the planet's orbit gradually decays, dooming it to eventual spiral into its sun. It's a cosmic balancing act. Too weak a field and the star strips the atmosphere away. Too strong and the planet risks self-destruction. For astronomers, these exotic worlds are more than curiosities. They're testing grounds for theories about how magnetism shapes planetary evolution. By studying how hot Jupiters interact with their stars, we're glimpsing the extremes of what's possible in planetary science. And who knows, one day, we might point a telescope at a distant star and catch the flicker of an alien aurora, a beacon from a world where magnetism doesn't just shape the weather, but rewrites the rules of what a planet can be. Most stars live quiet lives, slowly burning through their fuel over billions of years, but HD 45166 is a ticking time bomb. This Wolf-Rayet star, a seething ball of helium and heavy elements 6,000 light-years away, isn't just unusual, it's rewriting our understanding of stellar death throes. What makes it special? A magnetic field 100,000 times stronger than Earth's, so intense it's literally tearing the star apart from within while setting the stage for one of the universe's most violent transformations, the birth of a Magnetar. Wolf-Rayet stars are already rare cosmic rebels, massive stars that have shed their outer hydrogen layers, exposing their scorching helium cores. But HD 45166 stands out even among these outliers. Observations reveal its surface is wrapped in magnetic loops so powerful they've corralled the star's own stellar wind into twin jets streaming from its poles like cosmic blowtorches cutting through space. These aren't gentle outflows, they're torrents of ionized gas moving at over 3,000 kilometers per second, sculpted by magnetic forces that would shred any nearby planet in moments. How did this star become so magnetically charged? The answer lies in its turbulent past. Unlike typical stars, where magnetic fields are generated by churning plasma in their outer layers, HD 45166's magnetism might be the legacy of a cosmic merger, two massive stars colliding and combining their magnetic fields in a violent embrace. The resulting tangled field lines were then amplified as the merged star's core contracted, compressing magnetism to levels rarely seen outside neutron stars. This isn't just a star with a strong magnetic personality, it's a stellar Frankenstein, stitched together from the remnants of a catastrophic dance. But the real drama lies in its future. Within the next 100,000 years, a heartbeat in cosmic time, HD 45166, will exhaust its nuclear fuel and collapse under its own gravity. When it does, that colossal magnetic field won't disappear, it'll be squeezed into a neutron star no larger than a city, creating a newborn Magnetar with a field a quadrillion times Earth's strength. Simulations suggest the resulting object could be one of the most magnetic neutron stars ever formed, a cosmic powerhouse capable of unleashing flares bright enough to sterilize nearby star systems. What's truly fascinating is how this star challenges our models. Until HD 45166 was studied, astronomers assumed such extreme magnetism only appeared after a star collapsed into a neutron star. Now we're seeing the universe can forge magnetic monsters before the collapse, meaning the Magnetars we observe today might have been born from stars even wilder than we imagined. Every flicker of this star's light, every twist of its magnetic jets is a preview of the cosmic spectacle to come, a stellar death that doesn't just fade quietly, but leaves behind a magnetic legacy that will shape its corner of the galaxy for millions of years. Some stars don't just explode, they erupt with a magnetic fury so intense it reshapes their entire death. Take supernova 1987A, the closest stellar explosion witnessed in modern times. While most supernovae detonate when their cores collapse under gravity, this one might have had an extra hidden trigger, a catastrophic magnetic rebellion deep inside the star. Imagine a dying sun, its core racked by instability, when suddenly its own magnetic field turns traitor, twisting into knots so tight they act like cosmic detonators. The result, an explosion that doesn't just blast material into space, it flings it outward in jets sculpted by magnetic forces, turning a spherical burst into a cosmic hourglass of destruction. The evidence lies in the debris. When astronomers studied the remnants of supernova 1987A, they noticed something peculiar. Instead of expanding evenly in all directions, the ejected material formed distinct lobes and rings as if guided by invisible hands. These structures matched simulations where a star's magnetic field, amplified to extreme levels during its final moments, channeled the explosion along two opposing jets. It's like squeezing a balloon until it pops, except the balloon is a star, and your fingers are magnetic fields strong enough to dictate how it tears itself apart. What could cause such magnetic mayhem? The answer lies in the star's spin. Unlike our sun, which rotates sedately, the progenitor of supernova 1987 was likely a rapid spinner, a blue supergiant whirling so fast that its core became a dynamo on steroids. As the star neared death, convection currents in its interior stretched and wound magnetic field lines like overwound clock springs. When the core finally collapsed, those pent-up fields didn't just vanish, they snapped back violently, injecting extra energy into the explosion and launching material at velocities gravity alone couldn't explain. This magnetorotational mechanism isn't just theoretical. Recent observations of other supernovae, like 2004 DJ and 2006 J, reveal similar asymmetrical ejector and polarized light signatures, both hallmarks of magnetic influence. Some even show telltale gamma-ray bursts, the universe's brightest flashes, which are thought to arise when magnetically collimated jets punch through a star's outer layers at near light speed. These magnetic supernovae aren't just louder than their ordinary cousins, they're fundamentally different, their explosions orchestrated as much by invisible fields as by gravity's crush. But the wildest twist, these magnetic instabilities might solve a cosmic mystery. For decades, astronomers puzzled over how some supernovae produce heavy elements like gold and uranium. Traditional models couldn't explain their abundance until magnetism entered the picture. In a magnetically driven explosion, turbulent mixing between the star's layers creates perfect conditions for rapid neutron capture, the process that forges the universe's heaviest atoms. Supernova 1987A's debris, for instance, contained shocking amounts of nickel-56, an isotope linked to extreme magnetic compression. It's a stellar alchemy that only unfolds when magnetism stirs the cauldron. What's humbling is realizing these magnetic supernovae might be more common than we thought. As telescopes grow sharper, we're spotting more asymmetric remnants and polarized light curves, hints that magnetism could be a silent partner in many stellar deaths. And if that's true, it means our understanding of how stars live and die is still evolving, rewritten by the invisible force that shapes everything from atoms to galaxies. So the next time you see a supernova's afterglow, remember, you might be witnessing not just a star's end, but the final, fiery act of a magnetic revolt that began deep in its core. The Crab Nebula isn't just a cosmic debris field, it's a machine. At its heart lies a pulsar spinning 30 times per second, its furious rotation and magnetic field working in tandem to power an engine that's been running non-stop for nearly 1,000 years. This isn't just stellar afterlife, it's a magnetospheric eternal engine, a celestial dynamo converting spin into light on a scale that defies human ingenuity. Every second, the pulsar loses a tiny fraction of its rotational energy, and that loss lights up the entire nebula like a fluorescent bulb wired to a neutron star's heartbeat. The mechanics are both brutal and precise. As the pulsar spins, its magnetic field, trillions of times stronger than Earth's, whips charged particles into a frenzy, accelerating them to near-light speeds along tightly wound spiral paths. These particles then slam into the surrounding nebula, their kinetic energy transforming into the eerie blue glow that makes the crab so iconic. But here's the twist: this isn't a one-time explosion's afterglow. It's a continuous refueling where the pulsar's gradual spin-down acts like a cosmic throttle, pacing the energy flow so the nebula never fades. Even now, nearly a millennium after the original supernova, the Crab Nebula shines brighter than entire star clusters, all because its deceased star left behind a magnetic generator instead of a corpse. What's staggering is the efficiency. The pulsar emits a relativistic wind, a supersonic stream of electrons and positrons that collides with slower-moving debris from the supernova. This collision creates a termination shock, a visible boundary where particles suddenly heat up and begin radiating synchrotron light. Hubble images reveal intricate structures in this zone, glowing filaments that twist like DNA and jet-like tendrils stretching light years into space. These aren't chaotic remnants, they're power lines shaped by magnetic fields into conduits for energy redistribution. The entire nebula functions like a grand electrical circuit, with the pulsar as its battery and magnetism as its wiring. Yet the true marvel is the timescale. Most supernova remnants fade within centuries as their ejecta disperse, but the crab's pulsar ensures its nebula will persist for millennia, its glow decaying only as the neutron star's rotation gradually slows. Even in 50,000 years, when the pulsar's spin has dwindled to a lazy crawl, its magnetic field will still be squeezing energy from every last twitch, illuminating the nebula long after most stellar explosions would have vanished into darkness. This process isn't unique to the crab. Pulsars like the one in the Vela supernova remnant or the bizarre Black Widow systems all convert spin into radiation through magnetic alchemy. But the crab remains the gold standard, a testament to how a dying star's magnetic legacy can outshine its life by orders of magnitude. For astronomers, it's more than a pretty light show. It's a masterclass in energy conservation, proving that even in death, stars can engineer immortality not through mass, but through magnetism's invisible hand. In the first fleeting moments after the Big Bang, the universe was a seething, superheated soup of quarks and gluons particles so energetic they refused to bind together, creating a plasma so dense that light itself couldn't travel freely. Yet hidden in that primordial chaos, something extraordinary may have been stirring, the seeds of the universe's first magnetic fields. These weren't the vast, organized fields we see in galaxies today, but flickering eddies of electromagnetism, born from the turbulent motions of particles moving at near light speed. Picture this as quark-gluon plasma swirled and collided in the universe's first microseconds. Tiny imbalances in particle motions could have generated weak currents like cosmic static electricity. These currents, amplified by the universe's rapid expansion, might have woven the first fragile threads of magnetism into the fabric of space-time itself. But how could something as delicate as a magnetic field survive the violence of the early universe? The answer lies in plasma's stubbornness. In those first moments, the universe was so hot that particles were ionized, their electrons stripped away, creating an electrically conductive medium where magnetic fields couldn't easily dissipate. Once formed, these fields were effectively frozen in, carried along by the plasma's motion like invisible ink mixed into a cosmic river. Even as the universe cooled and quarks combined into protons and neutrons, those magnetic imprints could have persisted, stretching and thinning but never fully vanishing. It's a bit like blowing smoke rings into a hurricane. The structure might warp and twist, but traces of the original pattern remain. The real turning point came during cosmic inflation, the universe's brief but explosive growth spurt. In less than a trillionth of a second, space expanded faster than light, stretching quantum fluctuations from microscopic to astronomical scales. If even faint magnetic fields existed before inflation, they would have been magnified to intergalactic proportions, like a tiny scribble enlarged to cover an entire mural. Some theories suggest this process could explain why galaxies today show coherent magnetic fields spanning tens of thousands of light-year structures, too vast to have formed solely from local stellar processes. These fields might be cosmic fossils, relics of magnetism's earliest moments preserved in the voids between stars. Evidence for this idea comes from an unexpected place, the cosmic microwave background, the afterglow of the Big Bang itself. While the CMB doesn't directly show magnetic fields, its polarization patterns, the way its light waves vibrate hint at turbulent motions in the early universe that could only arise if magnetism were already at work. Some models even suggest that primordial fields might have left subtle distortions in the CMB's temperature fluctuations, like invisible hands gently pressing on the fabric of spacetime. Detecting these fingerprints is extraordinarily difficult, but next-generation telescopes like the Simons Observatory are searching for them, hoping to catch glimpses of magnetism's cosmic debut. What's truly mind-bending is how these nascent fields might have shaped the universe's evolution. In the darkness before the first stars ignited, weak magnetic fields could have acted as cosmic scaffolding, guiding the collapse of gas clouds into the filaments and nodes that later birthed galaxies. Without them, matter might have remained too diffused to clump efficiently, delaying or even altering the formation of the cosmic structures we see today. It's a humbling thought. The same invisible forces that power neutron stars and light up auroras might have been quietly directing the universe's growth since the dawn of time. Yet mysteries remain. Did magnetism arise spontaneously from quantum fluctuations, or was it sparked by phase transitions, cosmic snaps like water freezing into ice as the early universe cooled? Could these fields explain anomalies like the unexpected alignment of quasar light polarizations across billions of light years? The answers might lie in tabletop experiments with quark-gluon plasmas, where physicists recreate fractions of the Big Bang's energy to probe how magnetic fields emerge from particle chaos. Every new discovery peels back another layer of this cosmic origin story, revealing how even in its infancy, the universe was already crackling with electromagnetic potential, a hidden force waiting to sculpt the galaxies, stars, and planets yet to come. The sun doesn't just light up the solar system, it weaves an invisible shield stretching billions of miles into the void. This is the heliosphere, a colossal magnetic bubble blown by the solar wind, where the sun's influence doesn't just dwindle, it rebels against the interstellar medium. Picture the solar system hurtling through the galaxy at nearly 250 kilometers per second, plowing into a soup of cosmic rays and ionized gas. Without the heliosphere's magnetic defenses, these interstellar particles would bombard planets like machine gun fire, stripping atmospheres and sterilizing surfaces. But the sun's field doesn't just stand guard. It builds a highway, channeling and redirecting chaos into a structured flow that protects every world in its gravitational grip. At the heart of this system lies the heliospheric current sheet, a sprawling, wavy boundary where the sun's magnetic polarity flips, a ripple in spacetime shaped like a spinning ballerina's skirt. This sheet isn't static. It rotates with the sun, warping into spirals as particles ride its folds like cosmic surfers. Charged particles from the solar wind follow these magnetic contours, creating a labyrinth of lanes that stretch beyond Pluto. The result, a natural sorting mechanism where low-energy particles get trapped in magnetic pockets, while high-energy cosmic rays from deep space are deflected or slowed, like boulders filtered from a river. The real magic happens at the edge of the heliosphere, a turbulent frontier called the heliopause. Here, the solar wind's outward pressure collides with interstellar winds, creating a shockwave akin to a sonic boom in slow motion. Voyager spacecraft, the only human-made objects to breach this boundary, recorded something astonishing. Even in interstellar space, the sun's magnetic field lingers, tangled with alien fields from the Milky Way. It's not a clean border. It's a frothing magnetic foam where solar and interstellar fields reconnect in bursts of energy, sometimes allowing galactic rays to sneak through before being hurled back into the void. Yet this magnetic highway isn't just a barrier, it's a dynamic filter. During solar maximum, when the sun's field is most chaotic, the heliosphere swells, tightening its grip on cosmic rays. During solar minimum, it weakens, letting more interstellar particles slip through. These fluctuations leave fingerprints in unlikely places. Tree rings show traces of carbon-14 spikes when weakened solar magnetism allowed more cosmic rays to reach Earth, altering atmospheric chemistry. Even Earth's cloud cover might subtly shift in response to these interstellar intrusions, linking the sun's magnetic mood swings to climate patterns over millennia. The irony, this cosmic shield is shaped by fragility. The solar wind, a mere whisper of particles compared to interstellar pressures, should be overwhelmed. But magnetism amplifies its reach, turning a faint breeze into a structured force field. It's like using a desk fan to push back a hurricane, only to discover the fan's breeze has been magnetically coiled into an impenetrable wall. And as the sun journeys through the galaxy, encountering denser interstellar clouds or the ghostly magnetic remnants of long-dead stars, the heliosphere breathes in and out, its boundaries flexing to adapt, a testament to the quiet power of organized magnetism in the chaos of space. For astronauts, this highway is both protector and puzzle. Missions to Mars must account for these magnetic tides, as weakened heliospheric protection during solar minimum could turn a 2-year voyage into a radiation gauntlet. Meanwhile, astronomers study the heliosphere's structure for clues about other stars, because if our sun's field creates this intricate shield, surely others do too. The heliosphere isn't just our solar system's cloak. It's a prototype proving that even a single star's magnetism can sculpt the void into a sanctuary. Neutron stars don't just spin with perfect cosmic precision, sometimes they stutter. Astronomers call these sudden speed-ups glitches, and they're some of the most bizarre behavior we've observed in the universe. Picture a skater pulling their arms in to spin faster, except this skater is a city-sized stellar corpse weighing more than our sun, and its sudden burst of acceleration isn't caused by movement, but by the chaotic interplay of quantum mechanics and magnetism deep inside its core. These glitches aren't subtle. In 2019, the Vela pulsar, a neutron star spinning 11 times per second, suddenly revved up by a fraction of a percent. That might sound tiny, but for an object with the mass of a sun compressed into a sphere smaller than Manhattan, it's like slamming on a cosmic gas pedal. The energy released in that split-second adjustment could power human civilization for centuries, and Vela isn't alone. Over 300 pulsars have shown similar hiccups, some speeding up, others slowing down unpredictably, as if their internal mechanics were governed by invisible hands. So what's really happening inside these stars? The answer lies in a quantum phenomenon called superfluid vortices. Beneath a neutron star's rigid crust of iron nuclei, squeezed into a lattice harder than diamond, the core is a surreal ocean of neutrons flowing with zero friction, a superfluid. When the star forms, this superfluid spins rapidly, creating microscopic whirlpools called vortices. Normally, these vortices align with the star's rotation, keeping pace like synchronized dancers. But here's where magnetism throws a wrench into the works. The star's colossal magnetic field, trillions of times stronger than Earth's, penetrates the superfluid, pinning some vortices in place like cosmic anchors. Over time, as the star's crust gradually slows due to magnetic braking losing energy by beaming radiation into space, the superfluid's vortices try to keep spinning at their original speed. Tension builds until suddenly the pinned vortices unlock, transferring their pent-up angular momentum to the crust in a violent jerk. It's like snapping a twisted rubber band. The stored energy releases all at once, and the star's surface lurches forward. The result, a glitch that can make a pulsar's spin rate jump in less time than it takes to blink. But the story doesn't end there. Some glitches come with electromagnetic fireworks. In 2016, a Magnetar named 1E10487-5919 exhibited a glitch accompanied by a burst of X-rays, suggesting its magnetic field actively participated in the upheaval. Theorists now suspect that in magnetars, where magnetic fields are strong enough to distort spacetime, glitches might trigger Starquakes ripples in the crust that release energy not just as spin changes, but as high-frequency radiation. What's astonishing is how these events bridge scales. The vortices responsible for glitches are quantum objects, each barely wider than an atomic nucleus. Yet their collective behavior reshapes the rotation of an entire star, sending measurable tremors across the galaxy. For physicists, glitches are cosmic laboratories, offering glimpses into how superfluidity and magnetism interact under conditions impossible to replicate on Earth. Every unpinned vortex, every sudden spin-up, is a clue to the hidden machinery powering the universe's most extreme objects. And here's the kicker: glitches might help solve a deeper mystery. By studying how often they occur and how much energy they release, astronomers can probe the internal structure of neutron stars, determining whether their cores contain exotic matter like hyperons or free quarks. It's a bit like listening to a washing machine spin cycle to deduce what's inside. The noise of glitches reveals the invisible. So the next time a pulsar's rhythm skips a beat, remember, you're not just witnessing a stellar hiccup. You're seeing the aftermath of a quantum rebellion, where the universe's strangest fluids and most powerful magnetic fields collide and rewrite the rules of spin in real time. The cosmic web isn't just a scaffold of galaxies, it's a vibrating network of magnetic symphonies. Woven between galaxy clusters, vast filaments of gas and dark matter stretch across the universe, but hidden within these colossal threads are Elfvane waves, ripples of magnetic energy that might act like cosmic power lines, transferring energy across intergalactic space. These aren't ordinary waves, they're vibrations in the very fabric of the universe's magnetic fields, moving through ionized gas so tenuous it makes Earth's atmosphere seem dense by comparison. Imagine plucking a guitar string, except the string is a million light-year-long tendril of plasma, and the note it plays could determine how galaxies evolve. These waves get their name from Hans Elfvane, the Nobel Prize-winning physicist who first predicted them in 1942. On Earth, They're observed in laboratory plasmas and even in solar flares, where they help channel energy across the sun's corona. But in the cosmic web, Alfvén waves operate on a scale so vast it defies imagination. Picture a galaxy cluster weighing a quadrillion suns. Its gravity pulls surrounding gas into filamentary rivers. As this gas flows, it drags magnetic field lines along with it, creating tension. When those lines snap back, like overstretched rubber bands, they generate Alfvén waves that race along the filaments at thousands of kilometers per second, carrying energy from bustling galactic hubs to the quiet voids between. The implications are staggering. Normally, galaxy clusters, the universe's largest gravitationally bound structures, are thought to grow by slowly accreting gas. But Alfvén waves offer a shortcut. These magnetic ripples could transport energy from active, star-forming regions into the quieter outskirts, heating gas that would otherwise cool and collapse into new stars. In essence, they're cosmic regulators, ensuring some parts of the universe don't burn too bright or fade too fast. Observations of the Perseus cluster, for instance, show faint, spiral-shaped patterns in its X-ray emissions, ghostly fingerprints that might be the aftermath of an Alfvén wave passing through, gently stirring the cluster's gas like a spoon in a cup of coffee. What's truly bizarre is how these waves interact with cosmic rays, the high-energy particles zipping through space. As Alfvén waves propagate, they create microscopic turbulence, scattering cosmic rays and altering their path. Some researchers believe this process could explain why distant galaxy clusters show unexpectedly even distributions of cosmic rays, rather than clumps around their sources. It's as if the cosmic web's magnetic waves act like cosmic DJs, remixing the universe's particle traffic into a smoother flow. Yet detecting these waves directly is a monumental challenge. The plasma between galaxies is so diffuse that Alfvén waves there are extraordinarily faint, their signals drowned out by brighter astrophysical phenomena. But astronomers have found clever workarounds. By studying how radio emissions from distant quasars twist as they pass through the cosmic web, a phenomenon called Faraday rotation, they can map magnetic fields along these filaments. Combined with simulations, these observations hint at wave-like patterns, subtle undulations in the magnetic fabric that align with Alfvén's predictions. The deeper mystery, these waves might be more than just energy transporters, they could be architects. Some theories suggest Alfvén waves in the early universe helped amplify weak magnetic seeds into the large-scale fields we see today, essentially building the universe's magnetic infrastructure from the ground up. If true, it means the same forces that now gently heat galaxy clusters once played a role in shaping the cosmos itself, turning randomness into structure through the quiet, relentless push and pull of magnetic vibration. So while the cosmic web's gravity gets all the attention, its magnetism whispers just as loudly if you know how to listen. Every ripple, every invisible wave is a thread in the universe's grand tapestry, connecting galaxies not just by gravity, but by the unseen currents of magnetic energy that flow between them. And as we learn to decode these signals, we're uncovering a universe far more dynamic and far more interconnected than we ever imagined. Wormholes aren't just science fiction. They might be cosmic shortcuts held open by the universe's most extreme magnetic fields. According to some solutions of Einstein's equations, these hypothetical tunnels through space-time wouldn't stay stable without something counteracting the crushing force of gravity. That's where magnetism comes in. Imagine a black hole's gravity trying to snap a wormhole shut like a rubber band, while an ultra-strong magnetic field pushes back, stretching the throat open like invisible fingers prying apart the fabric of reality itself. The math behind this is as wild as it sounds. General relativity allows for traversable wormholes, ones you could theoretically pass through, but only if they're lined with exotic matter possessing negative energy. Here's the twist: certain configurations of magnetic fields can mimic this exotic matter. In models like the Einstein-Maxwell theory, a magnetic field strong enough to distort spacetime could generate repulsive gravity at the wormhole's throat, preventing collapse. We're talking fields billions of times stronger than a Magnetar's, where the energy density warps the quantum vacuum into a stabilizing force. But how would such a field arise naturally? One possibility involves cosmic strings, theoretical relics from the early universe vibrating at ultra-high energies and generating magnetic turbulence powerful enough to twist spacetime into a tunnel. Another scenario pits two Magnetars in a lethal dance, their opposing magnetic fields interacting in ways that momentarily rip a hole in spacetime's fabric. Picture two hypermagnetic stars spinning in sync, their field lines braiding so tightly they puncture the continuum, creating a transient bridge between distant points in the galaxy. The catch, even if such a wormhole formed, surviving transit would require maneuvering through a maelstrom of magnetic chaos. Cross-sectional simulations show field lines inside the throat whipping around like electrified spaghetti, creating zones where charged particles get accelerated to near light speed. Any ship passing through would experience tidal forces from the magnetism itself, stretching atoms into noodle-like strings while polarizing every molecule on board. And at the exit, a deadly burst of gamma rays as the wormhole's magnetic energy finally discharges, like a cosmic capacitor unleashing pent-up fury. Yet these theoretical constructs aren't just physicist daydreams, they're testing grounds for unifying relativity and quantum mechanics. Wormhole models with magnetic stabilization predict observable side effects, like anomalous gamma-ray bursts with distinct polarization patterns. Some researchers even speculate that fast radio bursts, those mysterious millisecond flashes from deep space, could be magnetic wormhole echoes, remnants of microscopic spacetime bridges flickering in and out of existence. The most mind-bending implication: if magnetic wormholes exist even fleetingly, they'd rewrite the rules of cosmic travel. No need for warp drives or generation ships, just a carefully timed plunge into a magnetic vortex where the universe's own forces do the folding. Of course, the energy requirements are astronomical, and the stability is measured in fractions of a second. But in a universe where magnetism already bends stars and shreds atoms, who's to say it couldn't bend spacetime too? Until we prove otherwise, magnetic wormholes remain the ultimate what if, a reminder that even our wildest theories are just scratching the surface of spacetime's secrets. After exploring the universe's most violent magnetic powerhouses, from star-crushing Magnetars to galaxy-shaping cosmic fields, it's humbling to glance back at Earth and see what humanity has achieved in our quiet corner of the cosmos. Our strongest laboratory magnetic fields, like the 45 Tesla hybrid magnet at the National High Magnetic Field Laboratory in Florida, may seem feeble against a Magnetar's quadrillion Tesla grip. But make no mistake, these human-made fields are engineering marvels, pushing materials and physics to their absolute limits under conditions nearly as exotic as those found in deep space. Take that 45 Tesla hybrid magnet, a beast that combines superconducting coils with resistive electromagnets, consuming enough electricity to power a small town during operation. At full strength, its field is over 1 million times stronger than Earth's natural magnetism, powerful enough to levitate frogs, a quirky phenomenon called diamagnetic levitation, or halt a bullet midair if fired into the field's core. Yet what's truly revolutionary isn't just the raw strength. It's how these fields act as microscopes for quantum mysteries. When materials like graphene or high-temperature superconductors are placed inside, their electrons rearrange in ways that reveal secrets about quantum phase transitions, topological insulators, and even dark matter candidates. It's like using magnetism to peel back the layers of reality itself. But here's the cosmic irony. While nature's strongest fields rip atoms apart, our lab fields often create rather than destroy. In medical MRI machines, which operate at a mere 1.5 to 3 Tesla magnetic fields gently coax hydrogen atoms in our bodies to align, producing detailed internal maps without a single incision. Meanwhile, experimental fusion reactors like ITER use precisely controlled magnetic fields to bottle plasma at temperatures hotter than the Sun, attempting to replicate stellar power here on Earth. Even everyday technologies from electric car motors to maglev trains rely on humanity's mastery of magnetic principles that, elsewhere in the universe, manifest as apocalyptic stellar tantrums. The gap between natural and human-made fields, though vast, is narrowing. Recent breakthroughs in superconducting materials and pulsed magnet technology hint at future machines breaching 100 Tesla sustainably, a threshold where scientists predict entirely new states of matter could emerge. Some theorists even speculate that with room temperature superconductors, we might one day approach the lower limits of astrophysical-grade magnetism in controlled settings. Imagine a lab where we could simulate neutron star crusts or recreate the magnetic reconnection, events that power solar flares, all within a secured facility on Earth. Yet perhaps the most profound lesson lies in the limitations. To match even 1% of a magnetar's field, we'd need energy densities that would vaporize any known material. Nature's extremes remind us that magnetism, for all our understanding, still holds quantum secrets we've barely glimpsed. Every leap in lab technology doesn't just advance engineering, it sharpens our questions about how the universe's most magnetic monsters truly operate. And somewhere between frog-levitating labs and star-quaking magnetars, the line between natural wonder and human ingenuity starts to blur, proving that even on cosmic scales, curiosity is the strongest force of all. From magnetars shredding atoms to galactic fields weaving the cosmic web, we've journeyed through 30 astonishing truths about the universe's most extreme magnetic forces. These invisible powerhouses don't just exist, they orchestrate cosmic chaos, bending space, birthing stars, and even rewriting the rules of physics. Picture this: a single teaspoon of magnetar material, weighed down by magnetic fury, could sink through Earth like a stone through fog. Or consider Jupiter's magnetic empire, so vast it could engulf the Sun, yet still dwarfed by the Milky Way's magnetic filaments, stretching between galaxies like cosmic puppet strings. We've seen how magnetism crafts universes within universes, how young stars use magnetic tendrils to feed, how black holes braid magnetic fields into light-speed jets, and how Earth's flickering field shields us from solar storms while painting our skies with auroras. Even the vacuum of space isn't safe from magnetism's grip. Near neutron stars, empty space itself polarizes, twisting light and conjuring particles from nothingness. And let's not forget the ultimate cosmic irony: wormholes, those hypothetical space-time tunnels, might rely on magnetic fields trillions of times stronger than Earth's just to stay open for a fraction of a second. But here's the thrilling part: we're only scratching the surface. Every discovery, from Starquakes echoing across galaxies to ancient magnetic fossils hiding in tree rings, hints at deeper layers to unravel. Could primordial magnetism have seeded the universe's structure? Do magnetic monopoles lurk inside magnetars? The next decade of telescopes, from the square-kilometer array to lunar observatories, promises answers that might rewrite textbooks. So tell us, which fact bent your mind the most? Was it the Black Widow pulsar slowly devouring its companion, or the Sun's magnetic butterfly diagram painting its tantrums across centuries? Drop your favorite in the comments, and if you're hungry for more cosmic wonders, hit subscribe. Because in a universe where magnetism shapes everything from atoms to infinity, the next revelation is always just one magnetic storm away. The cosmos whispers its secrets in magnetic code. We're just learning how to listen.